I'm going to. I was asked today to talk about a little bit about my journey in science, but also, of course, about some of the discoveries that we've made along the way. And I thought an interesting way to do that would be to start by telling you exactly how I became interested in trying to understand consciousness. And really, it was a single event that led to what has become now a 25-year journey for me, something that one might call the search for consciousness. And it began just after I finished my postdoctoral studies. And as Robin just mentioned, that was in Montreal at the MNI under the mentorship of Dr. Michael Petrides. And with Michael, I had been studying the frontal lobe using techniques like positron emission tomography, or PET, and functional magnetic resonance imaging, or fMRI, to try and understand how the frontal lobe is organized specifically for working memory processes. In '97, immediately following that postdoc, I just returned back to Cambridge in the UK. And I was introduced to a young patient. Her name was Kate. She was a school teacher from Cambridge. And at the time I was introduced to her, she had been diagnosed as being in a vegetative state. Now, this is a condition in which patients have, their eyes will often open. They'll go to sleep and close their eyes. They'll often have sort of roving eye movements as they look around the room, but they absolutely importantly will never respond to any form of external stimulation. And Kate was exactly like this. If you asked her to blink her eyes, nothing would happen. If you asked her to look this way or that way, she wouldn't do it. Wiggle her toes, she would do no responses at all to any external prompting. She got into this condition because she'd contracted a virus that had attacked her brain. First, she lapsed into a coma and eventually emerged into what we now usually refer to as a vegetative state. Now, together with my colleagues in Cambridge, we thought, well, isn't there something we can do with brain scanning with a patient like Kate? And up until that point, really nobody had ever thought to put a patient like this into a scanner to see what might be going on inside their brains, because of course the assumption had always been that they are vegetative, they're in a vegetative state, we're going to see nothing. We had to put together a study very quickly. We had about 24 hours to do this, and at the time we were using an early imaging technique, positron emission tomography, or PET, as you can see it here. This is Addenbrooke's Hospital in Cambridge. What we decided to do was to show Kate a very active visual stimulus. Now remember, this is 1997. This was the standard Windows screensaver, and it actually served as a very good experimental stimulus for us because it involves lots of color, lots of movement, and we knew that if we were going to see anything, this sort of stimulus would probably be quite good at activating the visual cortex. Now, I'm sure you all know this, just to make sure you're all oriented in the right direction. The visual cortex is at the back of the brain. And the idea here was that if there was anything at all going on in Kate's brain, then perhaps we would be able to pick up some responsivity, some activity in the visual cortex. And that's exactly what happened. As you can see there, a very bright red blob at the back of Kate's brain, exactly where you'd expect it to see if her brain was responding to this visual information. Now, what I also found very curious was that we saw some activity at the front of the brain. You can see it there in the dorsolateral frontal cortex and the premotor cortex. And these are areas that actually I had been working on back in Montreal just a year earlier, looking at how these regions are involved in various conscious processes like planning and thinking ahead and decision making and working memory, as I mentioned earlier. And it started me wondering, well, is there something more going on for patients like Kate? Maybe it's not just an automatic response in the visual cortex. Maybe there's more going on. So the following day, we decided to probe Kate a little bit further and see whether her brain would respond to familiar faces. Now, many of you probably know about the FFA, or the fusiform face area. It's at the bottom and at the back of the brain, and this is an area of the brain that is specialized for perceiving faces. Now, what we thought we would do is show Kate pictures of faces of her friends and family and compare it to scrambled images that had the same basic color and light dark contrast, but nevertheless had no face information. Now, when you do this sort of study in a healthy participant in the scanner, you'll see exactly what you can see here on the left-hand side. Typically, when you compare those two conditions, the fusiform face area will light up brightly. And here's what we saw in Kate's brain. Again, it looked very, very similar to a completely healthy person. And you have to bear in mind here that at this point, Kate had supposedly been in a vegetative state for 5 or 6 months. Yet, when we showed her pictures of her friends and family in the scanner, her brain responded almost exactly as the brain of a healthy participant would respond under the same situation. And again, I was really intrigued by this, and it really started to make me think, well, you know, perhaps there's more going on for these patients. Maybe the vegetative state isn't really a vegetative condition at all. Perhaps there's something else that we can find in this patient group. So over the next few years, I recruited more and more patients who had been diagnosed as being in a vegetative state. And we tried all sorts of different things. We tried to do things to them in the scanner, like in this example, we would play them speech. And here we were simply looking to see whether the brains of any of these patients would respond to the contents of speech. And we did this by comparing stimuli, just spoken words or spoken sentences, with scrambled versions of those stimuli that didn't sound like speech at all. And again, if you look at the top left and the top left column there, you can see what happens in healthy participants when you do this sort of contrast. The brain is very good at detecting speech as speech. That is, it detects it as something different to other sounds. And typically you see activity on both sides of the brain, but predominantly on the left, that involves the planum temporale and Heschel's gyrus. Here's a whole array of patients. Each one of these pairs is a different patient who had been diagnosed as being in a vegetative state. And as you can see, it was really rather common that we would see these speech-specific responses. That is, as you can see there in the pie graph at the bottom, about half of patients who appeared to be entirely vegetative in the scanner would produce these interesting responses with their brains. And this was really the first time that we started to become aware that many of these patients may not be exactly what they appear to be clinically or behaviorally. Now, the other thing about this data is that the extent of fMRI activity also predicted whether any of these patients would recover. And of course, this is extremely important. One of the big dilemmas about making long-term decisions for these patients is asking the question, well, is there any possibility that any of them are going to recover? And one thing that we saw in this patient group is that the level of fMRI activity, so if you like, the more elaborate your brain activity was in response to these speech stimuli, the more likely you would be to show some signs of recovery 6 months from now. So this was the earliest sign that we had that this imaging data, this fMRI data, could provide some prognostic information, some information that we could use to predict which patients would recover and which wouldn't. But still, in the back of my mind, this question of consciousness was really there, and I would really started to get concerned about the fact that some of these patients may even have levels of awareness that we might even be able to detect with techniques like fMRI. And one thing that very much, if you like, took the wind out of our sails back in those days was this study that I carried out with colleagues in Cambridge, including Matt Davis, who's the first author here. And here what we did is we took the task that we developed for the patients, and we gradually, we took some healthy participants and we sedated them using the anesthetic agent propofol. And our idea here was, well, can we sort of mimic the vegetative state. Presumably, if these patients are truly vegetative, and by that we assume that they're not conscious of who they are and where they are and the situation that they're in, we could create a model of that by heavily sedating people with propofol. And as we were sedating them, we did the same, we exposed them to the same stimuli that we were now very used to exposing the patients to. And this is speech stimuli or signal correlated noise. And as you can see, as I reveal what happened here, as these healthy participants became more deeply sedated, very little changed in their brain. You know, sure, there are small voxels here and there. They're not exactly the same, but you wouldn't look at this and say, yep, in deep sedation, there is no speech perception. It's clearly just as strong. I mean, in fact, in some ways, it even looks stronger than in the awake condition. Sedating people to the point of them being unconscious, at least behaviorally unconscious, did not affect the brain activity in response to speech. And why was that so disappointing for me? Obviously, it's a very interesting scientific study, but for understanding patients in the vegetative state, it was really quite a disappointment, because here, if you look at this image of a vegetative patient and compare it to the deeply sedated healthy control, if we know that that healthy participant is not conscious, how can we draw any conclusions about consciousness in the patient on the right-hand side who is in a vegetative state? Clearly, we can't. I can spend a lot of time explaining to you why these results were as they are, but the bottom line is that speech perception is something that the brain does automatically. It is not something that you consciously decide to do. So you're all listening to me giving this lecture. None of you can decide not to process what you're hearing as speech. In fact, you can't decide not to understand it either. This is something that your brain is doing automatically. It is not under conscious control. And that was the real key that helped us decide what it was that we needed to do next. We needed to try and image something or produce a task that involved doing something that was only under conscious control, doing something that required consciousness to do it. And many of you will, I'm sure, will have read about the study that we published in 2006 by now, so I'm not going to dwell on it too long. But let me tell you a little bit about how we got to coming up with this idea of getting people to imagine playing tennis in the scanner. And I'm sure many of you have seen a medical drama on TV, or you've heard about a patient who's presumed to be unconscious, and the doctor will hold the patient's hand and say, "Squeeze my hand if you can hear me." And if the patient squeezes your hand or squeezes the doctor's hand, you know that they're conscious. Now, that's what clinically we refer to as command following. The patient has followed a command. You ask them to squeeze their hand and they did it. And the fact that they respond in this way is the key indicator, if you like, the thing that allows you to infer consciousness. Now, we know that vegetative patients cannot move voluntarily. If you ask them to squeeze your hand, they won't do it. But could they activate their brains voluntarily? And we tried many, many different tasks. And the one my colleague Melanie Bowley and I came up with at the time was to get people to lie in the scanner and think or imagine that they're playing a game of tennis. Now, that's not because there's a tennis playing part of the brain. It's simply because we wanted an easy way of getting people to imagine moving their upper body, their arms around vigorously as though they were playing a game of tennis. And this is because, as you can see here in healthy participants, this very reliably produces activity in the premotor cortex. If you ask somebody to imagine playing tennis, this area of the brain lights up. If you ask them to relax, activity in that area disappears. Now, amazingly, the very first patient that we tried this study on in the scanner produced almost exactly the same pattern of activity. She was a vegetative state patient. She'd been involved in a road traffic accident. She'd been vegetative for about 5 months at the time that we scanned her. That means she produced absolutely no responses to any form of external stimulation. Yet when we said, imagine playing tennis, this area of the brain lit up. And when we said, okay, now stop, just relax, activity in that area of the brain disappeared. and then we would do it again. In fact, you can see it here from this histogram on the right-hand side. These are 30-second epochs or intervals of time where we sequentially asked her just to relax or to play tennis, to relax, to play tennis. And what you can see is that activity in the premotor cortex shoots up every time she's playing tennis. And it was on this basis that we were able to conclude that this patient wasn't in a vegetative state at all. She was actually fully aware. She was aware of where she was, who she was, and the situation that she was in. Now, why do we feel so confident about making that decision? I mean, many people at the time said, you can't decide that somebody is conscious simply based on a pattern of brain activity. And let me give you a few pieces of evidence that we use to piece this jigsaw together. Now, the first one is again, a propofol study. This is what happens in healthy participants when you sedate them as you're asking them to imagine playing a game of tennis. And this is data from my colleagues, David Menon and Ram Adapa in Cambridge in the UK. So just look at the right-hand column. This is a view from above, looking at the brain from above. What you see in the awake condition is the premotor cortex responding when people are imagining playing tennis. But look, even at levels of low sedation, so these people are still more or less aware, but they're just sort of slightly groggy at this point. Here, the activity associated with imagining playing tennis has almost completely gone. And by the time that they're moderately sedated, it's disappeared completely. Of course, if you stop the infusion of propofol and let them wake up, suddenly they can imagine playing tennis again, and activity in the premotor cortex returns. So from this, we can, I mean, this is obviously only correlational, but we can conclude that when patients are unconscious, demonstrably unconscious, and sorry, when healthy participants in this case are demonstrably unconscious, they do not produce this pattern of activity related to imagining playing tennis. But there's actually, I think, a much better piece of evidence that came from a study that we were more or less made to carry out based on the reviewers' responses during our submission of the original science paper in 2006. And this is probably one of the strangest experiments I have ever conducted, but actually I think the results are really, really interesting. And it really shows you why voluntary action, whether it be a physical action of your body or an action in your brain, can be used as an index of consciousness. Now here, we put healthy participants in the scanner and we said, imagine playing tennis, just as we had done previously. And there you can see activation in the premotor cortex that we were now very familiar with. Then we scanned the participants again and we said, please do not follow any instructions that you hear. And then we gave them exactly the same stimulus that we'd given them previously. We said, imagine playing tennis. And as you can see, nothing happened. There was no activity in the premotor cortex, despite the fact that the instruction is absolutely identical. Nothing has changed between the two conditions, except that we previously instructed the participants to not do whatever it is we're about to tell you what to do. And that's because imagining playing tennis is not an automatic brain function. When I tell you to imagine playing tennis, you can choose to do it or choose not to do it. If you do it, it'll activate your premotor cortex. If you don't do it, it won't. And in this case, you know, we're very good at not doing exactly what we're told to do if we've previously been told to ignore the instructions, because these things are under conscious control. And the analogy I like to use is, you know, this is exactly the same as if this patient was able to raise her arm, for example. If you said, well, raise your arm if you can hear me, and she raised her arm, then you would conclude that despite other clinical information, she actually was conscious. And similarly, we had the same information. We had reliable and replicable brain activity that she could produce on command that told us that actually she was conscious and aware. Now, she obviously isn't alone. We've gone on to scan many patients, asking them to imagine playing tennis in the scanner. Here's a group of 10 patients, all activating the premotor cortex when asked to do so. And I can tell you that about 17%, so almost 1 in 5 patients who behaviorally appear to be completely unconscious, completely non-responsive. When you put them in the scanner, they can show that they're conscious by systematically activating their brains in this manner. So how could this be? Let's talk a little about the functional anatomy, if you like. How could a situation occur that you can imagine doing something like playing a game of tennis, but you can't actually produce those actions? And we have some very good ideas now about this. And this was work from one of my former postdocs here at UWO, Davinia Fernandez Espejo. Davinia conducted a series of very carefully controlled studies, starting with fMRI. And what she did is she asked the participants in the scanner, these were healthy participants, to both imagine playing tennis or imagine hitting a tennis ball and to actually hit a real tennis ball. So there was a tennis ball suspended in front, over the scanner. The participant had to reach out and actually go as if to hit it in one condition, and they had to imagine they were doing it in a different condition. And when you do the comparison between those two conditions, what you see is activity in the premotor cortex, but also activity in the motor cortex, in the contralateral hemisphere to the right side, which is where the movement was coming from, exactly as you would expect. So carrying out a movement over and above imagining that movement produces this activity in premotor, motor cortex, but also in the thalamus. Then Davinia used a technique known as dynamic causal modeling, or DCM, to try and model the interactions between these three areas of the brain and how those interactions are modulated when you go from imagining a task to actually performing that task. And it turned out that one particular connection from the thalamus to M1 to primary motor cortex, that excitatory connection is essential for the execution of purposeful movements in healthy participants over and above imagining that movement. So it's that thalamus to M1 connection that really allows you to go beyond thinking about doing something to actually doing it. There's one more piece of this puzzle required, and that is, well, can you show in a patient who is non-responsive, supposedly vegetative, but nevertheless able to imagine playing tennis, can you show that there's a problem in this particular pathway from the thalamus to M1? And that's exactly what Davinia did with her third study, which involved using DTI, or diffusion tensor imaging, to look at these tracks that connect this part of the thalamus to M1 and this part of the thalamus to the premotor cortex. And she took two patients who clinically were quite similar. Here the label is patient 1 and patient 2. Behaviorally, neither of them were responsive at all, but one of these patients we knew was conscious because he could imagine playing tennis. In fact, he could do far more, as I'm about to show you in a few moments. What Davinia showed is that in that patient, in patient 1 on the right-hand side, there was a systematic degeneration, if you like, of that pathway from M1, from the thalamus to M1, something that we did not see in patient 2, who clinically looked almost identical but showed no signs of consciousness in the fMRI scanner. So I think if you put these three pieces of information together, this excitatory connection from the thalamus to M1 seems to be really important for actually performing movements. And when you have problems or a damage to that tract in a patient, it produces this situation where you can imagine doing something because your pathway from thalamus to premotor cortex is still intact, but you cannot actually execute or carry out that movement. And this is the framework that we've been working in ever since, to try and understand why it is that some of these patients get caught in this gray zone, if you like, between consciousness and the vegetative state, where they are actually conscious and aware of everything going on around them, but nevertheless unable to signal that using any traditional behavioral means. Now, there was a next step in this journey, if you like, was to investigate whether we could actually use this technique to try and communicate with some patients who were supposedly in a vegetative state. And actually, it's a fairly simple next step. The idea was, well, could we just get these patients to imagine playing tennis to, for example, convey a yes, and to do something else with their brain to convey a no? Well, you might be asking, well, why didn't you just get them to think yes and think no? And the answer to that is that fMRI doesn't quite have, or isn't quite at the stage that we can differentiate between somebody imagining a yes and imagining a no. But we are at the stage where we can differentiate between people doing one complex motor task and another type of mental imagery. So this was a patient who had been in a vegetative state for 5 years. He was a patient of my colleague Stephen Lorry's in Belgium, and he was scanned by Stephen's team and by Martin Monti, one of my former postdocs working with me in Cambridge. What you can see there is that when he was asked to imagine playing tennis, this patient produced very convincing activity in the premotor cortex, looking very similar to the healthy participants. And then we tried a second task, which was to ask him to imagine walking around his house. And this is something that cognitive neuroscientists, psychologists often refer to as spatial navigation. And we know a lot about spatial navigation. We know that it involves the parietal cortex, but also the parahippocampal gyrus, an area that's often referred to as the parahippocampal place area. And if you look at the bottom left-hand side there, you can see a healthy participant activating the bottom blue blob is their parahippocampal gyrus while they're thinking about moving from room to room in their house. And indeed, this patient was able to perform exactly the same task. He produced a very similar pattern of activity. This is showing the lateral premotor cortex and the parahippocampal gyrus when he was asked to imagine moving around his house. Now, all of you, I'm sure, will have noticed that his brain looks very different. He has massively enlarged ventricles, and this is extremely typical of patients that have been immobile and classed as vegetative for many months. But nevertheless, there's no doubt, I think, that his pattern of activity was very similar to the pattern in healthy volunteers, whether he was asked to play tennis or asked to imagine walking around his house. So the next instruction for him then, once we'd established that he was conscious, was to say, well, we're going to ask you some questions. And if the answer is yes, think about playing tennis. If the answer is no, think about walking from room to room in your house. And Martin, my postdoc, started with some very simple questions that we could independently verify. I've changed the names here to preserve the patient's privacy, but it was questions like, is your name Scott? And of course, the patient knew that if the answer was yes, he would imagine playing tennis. And that's the pattern of activity that we saw there. And hopefully, you all agree that he was conveying a yes, because he knew that to say yes, he had to think about playing tennis. And this patient's name, in this case, was Scott. What about when we asked him a name that was not his real name? Say, is your name Andrew? In this case, he produced the contrasting pattern of activity, the two blue blobs in the lateral premotor cortex and the parahippocampal gyrus, that pattern that we know is associated with walking around the house or saying no. So he could tell us that he knew that his name, in this case, was Scott, and his name wasn't Andrew. He could tell us all sorts of other things, like places that he'd been to in the world prior to his accident. But we've gone on to use this technique very successfully in a number of patients to communicate with them and to ask questions that are much more pertinent to their general care and their potential wishes for the future. Here's an example. This is not from the same patient. This is a patient scanned here in London, Ontario, by my postdoc, Davinia Fernandez-Espero. And here we were concerned that the patient we were concerned with what the patient liked to do. I mean, you can imagine that for many of these patients, they get exposed to an awful lot of whatever it is they used to like before they got into a vegetative state. And this was a patient who'd been in this condition for 12 years. And as you might expect, very often the TV was put on and hockey was played. He was played hockey games. And the question we wanted to ask is, well, do you still like watching hockey? Maybe 12 years on, his tastes have changed. He doesn't want to watch hockey anymore. And as you can see there, he responded by imagining playing tennis by saying yes, he still liked watching hockey. We've also asked patients questions that are pertinent to their situations, like are you in pain is a question that we'll ask now very frequently, because if a patient is in pain, we have no way of knowing that. The patient can't tell us. I mean, the only thing I can imagine being worse than being stuck in this condition for 12 years would be to be in this condition and be in pain. And of course, we can deal with pain by administering analgesics. So in this case, this is the local patient. We said, are you in pain? And on 2 occasions, he responded by walking around his house and saying no. So you can communicate. There is no question at all that some of these patients are conscious, about 1 in 5, and you can communicate with them by getting them to answer simple yes and no questions, by imagining one task for a yes and imagining another task for a no. And this may seem cumbersome. It may not seem like the most elegant method of communication, but you have to remember that this is all that these patients have. Up until the point that we scanned them, they had no way of communicating with the outside world, no way of even telling people in the outside world that they were there at all. Yet we're able to detect consciousness with fMRI and to communicate with these patients, to have them tell us a little bit about their wishes and their needs. However, that said, this is far from perfect. And we know from a number of experiences over the last few years that many patients slip through the net. I've told you that 1 in 5 of them are likely to be conscious. That's assuming that we have a perfect, if you like, consciousness meter. And I don't think we have a perfect consciousness meter by any stretch of the imagination. I know we can do better. Getting people to imagine playing tennis for periods of time in the scanner does place a significant cognitive load on these patients. And it seemed obvious that some of them just wouldn't be able to do that, but might still have some level of awareness. And for the rest of my talk, I'm going to tell you how we've explored consciousness in the absence of command following. Can we get a consciousness in a way that doesn't require the participant to tell us that they're conscious, to follow commands? And some of the impetus for this work came from this patient who came to us after 3 months. He was in a vegetative state. He'd had an anoxic brain injury, which means that there'd been a period where his brain had been deprived of oxygen, and this had led to very severe brain damage, and he came to us supposedly in a vegetative state. We tried all our scans with him. We had him trying to imagine playing tennis in the scanner, and we could produce no activity at all, nothing to indicate that he had any consciousness at all. And you can see his mother there. I reported back to his parents at the time and said, yeah, I'm afraid we found no evidence at all that there's any residual awareness in your son. Obviously very disappointing news at the time, but several months later, when my research coordinator called the parents and just to check up on the patient, to find out how he was doing. This is something that we do with all of our patients. She was astonished to find that the patient was now learning to walk again. He was teaching himself to talk again. And very soon after this, he took himself back to college. He still had some physical challenges, but cognitively, mentally, there was no question that he had returned to exactly the state that he was before his anoxic brain injury. Now, this is extraordinary for a patient to go from appearing to be entirely vegetative to really making a comeback like this in a matter of months. It's something that I've only really seen once in my entire career. But of course, what I really wanted to know at the time was, did he have any memory about coming to London, Ontario and going through our scanning protocol? So we brought him back. We told him nothing about why, and we set a series of questions. We put together a series of questions that we would ask him about his experiences now at least 6 months before this, when he came to be scanned. And amazingly, he could answer every question. He knew what the scanner looked like. He remembered being in the scanner. He remembered what we'd asked him to do. He knew that we'd asked him to imagine playing tennis in the scanner. He remembered the names of my graduate students and my research team who'd worked with him at the time. He could even identify the color of the EEG leads that we put on his head one day. He remembered absolutely every detail. And more recently, when I interviewed him, when I was writing my book, and I went back to interview him, I said, well, how were you able to remember all this stuff? You remembered every detail of being scanned so many months earlier. And he said, I don't think anybody would be surprised. He said, well, I had nothing else to do. And here we have absolute proof of that a patient can appear to be completely vegetative, yet can be entirely aware, laying down fully fledged memories of every experience, every person, every conversation going on around him, despite apparently appearing to be completely vegetative. But more importantly, for the purposes of this this lecture, I would say what it showed us is that some patients slipped through the net. He wasn't able to imagine playing tennis, and we sent him home assuming there was no awareness, when obviously subsequently we learned that he was very, very consciously aware indeed. And so this sort of moved us into a different direction, asking the question, well, maybe, you know, the problem with this patient was that he was aware, he was conscious, but he just didn't quite have the cognitive resources to imagine playing tennis or imagine moving around his house. And so we moved into the direction of trying to decode consciousness from people's brain responses when they do something that is really completely non-effortful, and that is watching movies. And the movie that we use is an old Alfred Hitchcock movie. There are many reasons for that. One of them is that we like to try and find movies that people probably haven't seen before. But also, this movie is typical Alfred Hitchcock in that it's a story of a boy. You can see him here. He finds a toy gun. Sorry, he finds a real gun under his uncle's bed. You know it's a real gun, but you also know that the boy thinks it's a toy gun. And that's where the Hitchcock tension comes in. You can see it here. Hopefully you're able to see this video as it unfolds, but the tension builds as it becomes obvious that this kid is going to shoot somebody at some point. For him, he's playing an innocent game with a toy gun, but because many of your executive processes are working on this information, you know that it's a real gun. You also know that he thinks it's a toy gun. That's your theory of mind there. And you know, there are many intricacies of this plot that are really only things that you can really understand or follow if you are, you know, fully aware and fully conscious. Now, it turns out that if you put a lot of healthy participants into a scanner and have them watch a movie like this, many voxels in the brain are activated in synchrony. The brains line up. And let me give you a simple example of why that is. If a gunshot goes off, if you hear a loud gunshot, then all of everybody watching this movie, your auditory cortex is going to trigger at exactly the same moment. That's obvious because your brain responds automatically. What was intriguing about this movie and other movies like it is that many higher level cortical areas in the frontal and the parietal cortex are also highly synchronized across individuals. And I don't have time to go into how we were able to establish that. And this is work by, again, one of my former postdocs, Lorena Nachi, here in London. But Lorena did many experiments in healthy participants to demonstrate that this frontal and parietal synchrony, this activity that you see in everybody in frontal parietal cortex, is driven by us following the plot, by us understanding the twists and turns of the plot and what is going on. And what we can do is we show that we can pull apart the various networks in the brain that are being driven by this movie. Obviously, we've talked about the auditory network. The visual network is driven very strongly by the brain. But what I'm interested in is frontoparietal network. You can see it there in red. And this is just a sort of a simple example of what we've been able to show. But you can show that synchrony in this region is driven by particular moments of plot changes. When something important or significant happens in the plot, you get activity across all the participants in this area in this network of fronto and parietal regions. Now, work backwards from that and take into account other things that I've said about these patients. And I think it should become clear where we went next with this. Our reasoning went, well, if we can show that activity in these regions in a patient is also synchronized to healthy participants. What I mean by that is, if your frontal and parietal cortex is activating in a manner that is synchronized to healthy participants whilst you watch this movie, then it's reasonable to conclude that you are having the same conscious experience. And I will stick my neck out here and say, if you are having the same conscious experience during a movie, then there's no reason to believe that you are not having the same conscious experience in real life. And that's the background upon which we've arrived at this this technique that we use to decode consciousness, or find out that patients are conscious, just by looking at their brain activity while they're imagining playing tennis. Another piece of the puzzle here is, of course, what happens when you sedate people with propofol. In red on the left, you're looking at the auditory network, how that changes as healthy participants are gradually sedated with propofol. On the right-hand side, you're looking at what happens in the frontoparietal network. As I showed you right at the beginning of my talk, the auditory network or auditory regions are not affected by propofol sedation, and that is because these are not areas that are involved in consciously of conscious activity. On the right-hand side, frontal and parietal cortex, this activity in this region, or synchronized activity in this region, dissipates even when participants are mildly sedated. And I like to think of this as being the sort of neural equivalent of literally losing the plot. And if you want a sort of an analogous thing to think about, well, you know, we all drift off to sleep every night. Most of you have probably had the experience of somebody talking to you. We're often very aware that we're being talked to, or there are sounds going on in the room when we're half awake and half asleep. But it's exceedingly difficult to follow a complex movie plot. And I think that's exactly what you're looking at here. These higher order frontal and parietal regions that are driving the conscious experience are much more susceptible to sedation than primary sensory cortices in auditory and visual cortex, which are automatically responsive to whatever's going on in the outside world. And of course, I wouldn't be showing you this data if it wasn't that we've been able to use it to decode or detect residual consciousness in some patients who have otherwise been presumed to be in a vegetative state. These are two different patients than the one I showed you, the two I showed you previously. These were scanned by my postdoc Lorena. What she was able to do was to, in these two patients who clinically looked very similar, they both appeared to be in a vegetative state. She was able to look for which of these networks. Yellow is the auditory network, blue is the visual network, and red is the frontoparietal network. Which of these networks is intact and which is not intact in these patients? As you can see in patient one, only auditory cortex was synchronized with healthy participants. So that patient, we conclude, is having no conscious experience of the movie, but they are nevertheless, their brain is nevertheless still responding to auditory incoming information. On the other hand, patient number two had a pattern of synchronized activity that was startlingly similar to the group of healthy participants. Good activity in the frontal and parietal cortex that was absolutely locked to the time course of activity in healthy participants. And on this basis, we concluded that this patient actually was conscious. And of course, we didn't ask him to do anything. We just put him into the scanner and we played the movie. And based simply upon his brain's responses to that movie, we were able to conclude that he was aware. And of course, in other contexts, we went on to get him to imagine playing tennis. And in fact, he has even gone on to communicate a number of times with my team, using other techniques. So there is absolutely no question that this patient does have some residual consciousness, but we were able to detect it initially simply using this movie paradigm. I'm going to wind up now. I just thought I'd end my talk where I began, by talking about Kate, who was the first patient that we ever put in the scanner back in 1997. You know, it seems crazy to me now, now that we routinely, and in fact many other people also routinely, put these patients into scanners and get surprising results, finding patients that are conscious that people have thought they had lost years ago, even communicating with some of these patients. It seems amazing that this all came from this one patient, Kate, scanned in Cambridge in 1997. And it's amazing that what we know now, we knew none of this back then. But it's been a sort of a continuous journey of building blocks, gradually putting the next piece of the puzzle together, trying to work out what would somebody have to do for us to be able to conclude that they're conscious. And what I want to finish with is telling you what happened to Kate. Now, amazingly, Kate was another of the few patients I've seen over the years who made a very good recovery. Over the next few years, she taught herself to feed herself. She's recently, and this is now, of course, 20 years on, she taught herself to speak again. She wasn't able to speak immediately after she recovered, but she's learned to speak again. And there's no question that cognitively she's back to the Kate that she used to be. Again, like all of these patients, she has many physical challenges to contend with, but she did make a remarkable recovery, and she communicates very often. And I'll end this talk by showing you an email that she sent me. When I was writing my book in 2017, I went back to visit Kate in Cambridge, and we had a long chat. She was so pleased that she could talk again. And of course, I'd seen her many times over these 20 years, but she'd never been able to speak to me before. She used to use a letterboard, just push around letters with her fingers, but now she could speak again, and she was delighted. And we had something like a normal conversation. And she now, she types and she sends emails. And this is one of the things she wrote to me around the time I was putting my book together. She said, "The day you scanned me was the day I became a person again. It was the day that people stopped treating me like an object and started treating me like a human being. The scan was like magic. It found me." And the reason I'm going to end on this quote is I think it really sums up for me why I think this kind of research is so interesting to me, and also so fundamentally important, because consciousness defines who we are. And it's all there in this quote. When people thought Kate was unconscious, they actually stopped thinking of her as a person. And as soon as we scanned her, and whether the results of that scan told us she was conscious or not, I guess we'll never really know. But the moment we scanned her and saw evidence of something in there, some part of Kate was still there and was still responsive, that was the moment that people started treating her like a human being. And that's basically the way we think about consciousness is so centrally important to our sense of identity, our sense of self, and the way we think about ourselves and others. And without consciousness, I would argue, we are nothing. There are literally hundreds of people I could thank for work. I just included the people here whose work I specifically referred to in my talk. I've worked with some fantastic students over the years, students, postdocs, collaborators, senior staff. They've all contributed to this research. As Robin so very kindly mentioned during my introduction, I've written a book. It's not really a science book. I'd like to think of it as a science adventure into the grey zone. It really tells a story that I've just told you, how we gradually worked out how we could find these patients, start to communicate with these patients. And I tried to weave in some of the science, some of the early fMRI and PET studies into the patient stories, personal anecdotes of the patients themselves, and of course, some elements of what was going on in my life, my scientific journey, as I've come from, in this case, a postdoc to a rather seasoned PI. So thank you very much for listening. I hope I've given you something to think about.
Thank you, Dr. Owen. I think it's not an understatement when I say that everyone really adored your talk. I was checking the chats during, and everyone's really enjoyed your work. There's also a surprising amount of questions, so if you don't mind, we'll try to take a few.
I have as much time as you need.
Perfect. So I'll start with the most popular one. And so someone's asked, when you told patients not to follow instructions when imagining playing tennis, wouldn't you expect some brain area to actively inhibit this action? I'm surprised there was no activation.
Right. So, and that's a really important question. You have to know a little bit about how these early fMRI studies were done. So it's just a comparison. So it's not that there was no activity going on in the brain. It's that there was no additional activity related to the instruction to imagine playing tennis. So that is a very important point. And I can see if we had just done some sort of single scan, there would have been plenty of activity going on in the brain, because obviously these people are all thinking something. There's stuff going on in their heads. It's just that there's nothing that is specifically related to the instruction to imagine playing tennis.
The next question is regarding the thalamocortical connections you mentioned. So someone said some studies have shown that absence seizures also originate in those connections. Would you suggest that it might be the anatomical basis of consciousness?
So actually, that's a great question. So no, I don't think it's the anatomical basis of consciousness. I think it's probably the best way to think about it is rather like a disconnection syndrome. You've disconnected. It's not that connection per se is consciousness, but it's that by removing that connection or affecting that connection, you've somehow affected in this case the relationship between what somebody can think about and what they can do. So I think this is probably how we're going to solve consciousness in the long run. I don't think any serious neuroscientist these days believes that there's a part of the brain that is consciousness or does consciousness. It's going to be something to do with the interaction of different brain areas, and it's only by examining these extraordinary individuals that have these odd disorders of consciousness that I think we're actually going to get to the bottom of this.
Someone's asked, why was there such a huge gap in research from 1998 to 2007? Is it because of patient recruitment challenge, or are there any reasons?
There wasn't a gap at all. I mean, so this is more of a career question, really. It probably may not be meant this, but I just finished my postdoc. I had grant money to work on frontal lobe function, and suddenly I was introduced to Kate. And I had no money to pay for Kate to be scanned. Unfortunately, I had enough people around me with other grants that they could fund it. But I became quite obsessed with this whole idea. But I had no grant money to do it. So and this is expensive science. We have to transport patients around the place. We have to put them into scanners. We have to look after them and their families. And so it wasn't that we did nothing between 98 and 2006. It was that things were very slow to get off the ground. And I can tell you that I had absolutely no money to support this work until the science paper came out in 2006, when suddenly, my funding level increased dramatically. And I think it's because people realize this was a fundamental discovery. Up until that point, there's been a lot of I think sort of just disbelief that there was any point in pursuing this idea of these patients. And it was only when we really sort of hit the money, as it were, and showed that we can detect consciousness that things really took off. So we saw patients between 98 and 2006, but it was just one or two a year, as and when I could sort of put the pieces together to get them into the scanner and get them scanned.
As you mentioned in your book, towards the past few years, people actually contact you to have them scanned. So I guess it's become easier to find patients.
Yeah, I mean, literally back between 98 and 2006, we just had to wait until a patient in Cambridge had an accident. Somebody locally had an accident and ended up in the ICU in a vegetative state. It was just a waiting game. We couldn't afford to recruit them now here in Canada, things are very different. We get inquiries every week from people all over the country saying, can you scan my husband, my wife, my child, because they're supposed to be in a vegetative state. So things are much easier now.
Right. Matt Scarland asked, how often do vegetative state patients recover? And have there been any reports of patients waking up from vegetative states who can retroactively report on what they experienced during these experiments? I guess you mentioned one.
I did, and I have, but I should say, to put this in context, that is the only patient who has been able to report their experience that I've seen, and actually that I know of in the literature. It's very, the sort of literature and also Hollywood are full of, examples of patients waking up from comas after 25 years. That stuff typically, at least not in my lab, ever happens. These patients have all, to get into a vegetative state, you had to have had a very serious brain injury. And the chances of recovery are very low. And I would say over the last 25 years or so, of the some hundreds of patients I've seen, a handful have recovered. Maybe 3 or 4 or 5 have made any sort of meaningful recovery. And of those, there are only 2, Kate and the patient Juan, who I described, who'd recovered, who made what you could possibly call any sort of return to normal life, and only 1 has been able to report his experiences.
Yeah, that's quite an interesting moment in your book as well, to have him be able to report what he experienced.
Well, it is really important because it's one of those cases in science where you only need 1 example. And I can't emphasize this enough, right? There are many questions that you can answer with 1 person. The prevailing view prior to 2006 is that no vegetative state patients are conscious. In 2006, we unambiguously showed that one of them is, and that means that it could have been the only patient in the world, I suppose, but what are the chances of that happening? It at least shows you with 1 patient that it is possible that a patient can appear to be, appear to be unconscious, but actually is. And similarly with the patient who recovered, you only need 1 person to do this, to recover and tell you about it, to be absolutely certain that this can occur.
Next question. When you asked a patient to imagine playing tennis, did the SMA activation change substantially in every trial, or was the activation a result of averaging responses in many trials?
Yes, that's a very good question, and it's an important one. So typically the way we do that, and we modified the task over the years to sort of make it as efficient as possible. And so typically what we'll do is have somebody thinking about tennis for 30 seconds, relaxing for 30 seconds, thinking about tennis for 30 seconds, and we'll repeat that cycle 5 times. So they do tennis 5 times and relaxing 5 times. And the activity that you see is averaged, if you like. That's actually, it's a little bit more complicated than that, but it's averaged over that period. And it's actually important. It means that somebody can't just do it once. I mean, I did show the graph there of the patient whose activity was going up and down. And if a patient were to just do it once and then not do it at all, we probably wouldn't see significant activity. So you have to sort of consistently activate and deactivate for us to see that SMA blob. It is something that's exceedingly reliable, though. I can't overemphasize how reliable it is. I would say it's about as reliable in healthy participants as asking people to raise their hand.
The next question is a bit more, I guess, on the ethical side, perhaps. Do you believe that all patients with disorders of consciousness should be scanned to assess them?
So there are 2 answers to that question. The first is a sort of a pragmatic one, which is you can't scan every patient, and that's because for some patients scanning is not suitable. Obviously, if you have metal implants in your body, and many of these patients do because they've had serious accidents, then you'll often not be able to put them into an fMRI scanner because metal in the body is not compatible with being scanned. So some patients can't lie still. Movement is a big problem. If the patient is coughing and spluttering and has problems lying down, often these patients can't lie down without their without being able to sort of clear their airways. So there are many reasons why you can't scan everybody. There's also a more sort of philosophical thing, which is that some patients, you can look at their brain and say, well, I'm not going to learn anything from the fMRI in this patient. If the brain damage is so severe, I mean, imagine, take an extreme example. If your brain has gone completely, you are not going to have any consciousness, right? I mean, this is the architecture for consciousness has to be there. So in some cases, I would look at a patient and say, no, it's not worth it. But the second level answer to the question is generally yes. Generally yes. I think any patient that can go into the scanner and for whom scanning might tell you something, that is, that there's enough of their brain left intact, I think should be scanned, because this gives us information that is not available using any other method. This is entirely unique information that can, as I described in my talk, it can be prognostic. It can tell us who's likely to recover. It's certainly diagnostic. It tells us that these patients aren't what they appear to be. And I think that's tremendously important for patients and their families.
Right. The next question is, CIFAR seems like a unique institution. For those who don't know too much about it, could you tell us what it is about? Is it really different or not to standard funding systems in science?
I didn't get the first part of the question. Sorry.
So CIFAR, I'm not sure how to exactly pronounce it.
Yeah.
CIFAR.
Yes. So I am the co-director of the CIFAR program in brain, mind, and consciousness. It was previously co-directed by myself and Mel Goodale here at UWO. The new co-director, Mel, has just stood down recently. It's Anil Seth from Sussex in the UK, who, if any of you have done any work on consciousness, you'll know who Anil is. Yeah, so it is a really interesting different type of program. CIFAR funds networks of people. It doesn't generally fund the basic science. It funds people to get together and try and solve big problems. So we got involved in 2014 when they advertised for new programs. And the way it was advertised was, we want to know what the biggest problems are in the world and who would be the key people to bring together to try and solve those problems. And luckily enough, the application we put in was successful. And what that means is that twice a year, we get to hold a meeting of the CIFAR fellows who are all working in the area of brain, mind, and consciousness. And we debate and discuss issues like, are other animals conscious? And if so, is their consciousness like ours or not? Are neonates conscious? Young babies, are they conscious? Or how does their consciousness relate to ours? Machine consciousness, will we ever be able to make a machine that's truly conscious? And we do this by talking about it for a couple of days. We bring in guest lecturers who are experts in the specific field that we're talking about, and it's tremendous. I mean, I often say it's the only scientific meeting I get to go to twice a year where I really get to just think. I sit and I think about these questions and these these really big questions. So CIFAR is great, and I'll put a plug in here for our winter school. We started a CIFAR winter school on consciousness. We ran two at Montebello, which most of you will be familiar with, the border of Quebec and Ontario. Chateau Montebello, it's fantastic. We invite 30 or 40 senior graduate students, young postdocs, to come and meet the fellows in the program, talk about consciousness, hear about the latest research on consciousness. If you're interested in coming, we probably aren't going to be able to run it this year, probably because of the pandemic. We may find a way, but keep your eye on the CIFAR web pages for the Brain, Mind, and Consciousness Winter School, because it's a fabulous experience.
Thank you. And although we have a bunch more questions, I think we're gonna leave it at that, if that's okay. Thank you.
Fine.
Thank you very much, Dr. Owen, for joining us. We've linked in the conference guide some of your previous videos, the link into the gray zone. So if anyone wants to kind of look at those and hear a bit more about it, they can do that there.
Excellent. Thanks so much for listening, everybody.
Take care.
Thanks. You too. Bye now.